We will just use this whiteboard. Come on, little whiteboard. Okay, so new share. Oh, the whiteboard doesn't want to work either, so let's try this again. What a mess. Okay, so electrophilic aromatic substitution reactions, aromatic ring, reactive electrophile. We replace one of the protons on the aromatic ring with the electrophile. The mechanism is relatively straightforward, and I'm just going to do it with a little E plus, and later on we'll determine what E plus is, and that we can replace it with whatever it is. Okay, so the aromatic ring is going to attack the electrophile. This is going to make a system that looks like this. Oops. So there's an electrophile on the carbon that attack. There's still a proton there. And on the proton next door, so the way I've looped this blue arrow, it's the top carbon which is getting the electrophile. On the bottom carbon, it still has that proton there. But because the pi electrons have gone to make that bond with E, this carbon now has a positive charge. And of course, this positive charge is stabilized by resonance within the rest of the ring system. So the next step is that some Lewis base, so all we need here is a pair of electrons, is going to come along and grab this proton, and those electrons are going to go there to re-aromatize the ring. Now you're going to say to me, what's the Lewis base? Well, in each case, it's basically slightly different, but that is the mechanism. So yeah, basically that's it, and it's the same thing over and over and over again. So the various reactions that are talked about the most often are, actually we'll do it with just benzene in the middle here. So the first one is a nitration. And the two reagents that are used are nitric acid and sulfuric acid. So this is a nitration. in non-COVID years, you would have done this reaction in the lab. We do a little nitration reaction in the lab, which is kind of fun. Okay, so what's another reaction? Common reaction, bromination, Br2. And there's a catalyst which goes along with this, and it is normally iron tribromide. Yeah, so that's the most common one. And we just replace one of the protons with a bromine. Those lone pairs there. Chlorination, Cl2, iron trichloride. And we put substitute chlorine. Then there's two more, so bromination, chlorination. Organic chemists are interested in making carbon-carbon bonds, so let's do an alkylation. So RCl and aluminum trichloride. And this will put an R group on. This reaction is often called the Friedel-Crafts alkylation. So that's an alkylation reaction. And one more, very similar. And this time we are going to use our carbonyl, so an acid chloride. This is an acylation reaction. So an acyl group is basically this part here. So we're adding that there. So the Friedel-Crafts acylation reaction. Oh, I just remembered there's actually one more. So we've almost got our little web totally made out here. H2SO4, SO3, and this is a sulfonylation reaction. So we could make a sulfonic acid. So sulfonation. Now let's talk about making the various reactive electrophiles in each case. So probably the place we'll start off, the nitration, we'll do that one first. The chlorination and the bromination are very similar, so we'll do those basically together. And then we'll talk about the alkylation and the acylation reaction next. So the nitration. So this is interesting in the sense that you have got your nitric acid and your sulfuric acid. And you're reacting two really strong acids together. So which one is, when we've got, which one becomes the base, which one is the acid. This is the one which can mix people up a bit. So we'll do this first. So you're, in fact, the reactive electrophile is going to be NO2. And this means this nitrogen is going to have a positive charge here. So to get this, we need to lose what's going to become water. So if we protonate our nitric acid, we end up with this. And we generate a good leaving group. Then we'll boot out our water. And this gives us NO2 plus, and then plus water. And so this is our reactive electrophile. And when the aromatic ring attacks it, it can attack that nitrogen. So remember, the nitro group, when we draw it, is NO2. What does it look like? It looks like this. Right? So that ring can come in and attack the nitrogen. Those electrons are going to move up. And then the mechanism is exactly the same. And remember when you asked before, well, what's the Lewis base? Well, here's our little Lewis base there, water. So that's basically how you generate the reactive electrophile for the nitration reaction. So NO2 is the reactive electrophile. If we've got, for the halogenations, we have got our molecular halogen, which is going to be either the bromine or the chlorine. And we've got a Lewis acid, which we will call X3. So what happens here is that the Lewis acid, our transition metal, is going to be complexed with, so if we form a bond between X and FeX3, let's just make that bond. And then we'll have 3 X's off this. X, X, X. Now, if we were to draw formal charges on this, formal charges on this, this X, in the middle, this one's going to have a formal charge of plus, and our transition metal is going to have a formal charge of minus. Just think, X has got 7 valence electrons, so 7 minus 2 bonds is 5. 5 minus 4 electrons is plus 1. And so now this you can be considered your reactive electrophile. And your ring is going to attack not at that positive charge because you don't have a leaving group for it, but if it attacks the X bonded to it, so here, then these electrons can move on to the X, and that's the leaving group. So you would have your aromatic ring, X, still have an H here, H, positive charge, and you have iron X4 with a negative charge. And so this is in equilibrium with iron. that negative, that bromide, iodide, chloride can now, this little equilibrium here. And then now you've got your Lewis base to remove that proton and re-aromatize the ring. I should be drawing some blue, I guess. There we go. So yeah, so I guess the key point which I'd point out is where these arrows are in orange over here. So we're not attacking directly this X, which has got the positive charge. We're attacking next door. And so that makes that sigma bond can go over to the X. So we've got a leaving group. So this is basically a glorified leaving group. And so that's basically how the halogenation reactions work. There's two of those. Right. So before I move on, I guess I should ask. So the tricky part to both of these is just figuring out what the reactive electrophile is. So the nitration reaction, it's in fact the nitric acid which acts as the base, sulfuric acid acts as the acid. We generate a leaving group, which is the water. Then when the aromatic ring attacks, it's attacking the NO2 plus, the reactive electrophile. With the halogens, it's slightly different because there's no pi bonds in this. Be complex between our molecular halide and the iron tri, whatever halide it happens to be. That generates a leaving group and a reactive electrophile the ring can attack. And then you're going to re-aromatize the ring. So were there any questions on those two reactions first? Then we'll do the alkylation and acylation reaction, because those are the, there's a little bit more complexities to both of those, I think. Okay, then we will talk about the Friedel-Crafts reactions. So there's basically the alkylation and the acylation. Sorry, this is an E. Okay, now. This reaction involves your ring, and often it's alkyl chlorides. So some alkyl chloride and aluminum trichloride. And then our product will be, we're basically HCl. So whatever the chlorine is bonded to, this becomes the group that undergoes a substitution reaction. Now, aluminum trichloride, much like iron trichloride, is a Lewis acid. It's got that empty orbital. So when we're making our reactive electrophiles, this functions in very much the same way. So we've got our aluminum trichloride. Put on our lone pairs. So it's right underneath boron. So it's got this empty orbital here, empty p orbital. So let's donate our electrons in there. This will give us And if we put on our 4 more charges, the chlorine is going to be positive, the aluminum is going to be negative. Now, depending upon the type of alkyl halide we've got, so this can undergo a couple of different possible reactions. So if we do this, what we're going to form is aluminum tetrachloride plus a carbocation. Okay, so carbocations are very reactive, like, so these are very reactive electrophiles. Now, we have some rules about carbocations too, right? So somebody remind me of what makes which carbocation is the most stable out of this? A, B, or rank them, A, B, C, from most stable to least stable. Right. Okay. So so carbocation stability. So the larger the number of alkyl groups we've got, the more stable it is. So C would be the most stable. Most. This would be the least, because of these groups all donate inductively. And then there's hyperconjugation as well. Hyperconjugation. Now, when we did our SN1 versus SN2, all of that, we basically said in that part of the course, you don't form primary carbocations because they are too they're too reactive. I mean, they're too high in energy. So you could have a tertiary carbocation, you could have a secondary carbocation, you really wouldn't find a primary, and you really wouldn't find a methyl because they're too high in energy. So the interesting thing about this reaction is that if you try to do a Friedel-Crafts alkylation reaction with the primary alkyl halide, aluminum trichloride, erase that. So the group we are going to be adding is this group here, right? So we should make as our main product this. 1, 2, 3, 4. However, that isn't at all what when you do this reaction, this only accounts for 35% of your product. Your major product is in fact this. So still 4 carbons, but this counts for 65% of your products. So this reaction really doesn't, so with a primary alkyl chloride, you get these mixtures of products that don't really, that isn't helpful, particularly if you want this, this one. So how does this work? So if we were doing our mechanism, we would have, you would form your complex. And then let's make our carbocation. Positive. I really don't like doing this, in all honesty. Making this like that, to me, that sort of breaks all sorts of rules. Oh, I guess I should write what my formal charge is here. Positive. But if we had this carbocation, how would we get to form this product over here? What needs to happen to this carbocation so we can eventually make the major product in this reaction? What is it that we need to do? So this primary carbocation is high energy. Is there a way to make it lower energy? Yes, exactly. Hydride shift. So what we could do is if one of these hydrogens jumped over to the neighboring carbon, and I should actually, let's draw all of the protons on here just so it's clear. So we've got 2 protons plus the positive charge. So if we do a hydride shift, that will give us a secondary carbocation, and then the ring can react with the secondary carbocation. So and the Lewis base, in this case, we could have our aluminum tetrachloride. One of these chlorines can, got lots of lone pairs there, can jump off and grab that proton to make the HCl. So this is, we had our intermediate. One of these chlorines, just use that. Can grab that. That will give us our product. So the Friedel-Crafts reaction, this alkylation reaction, there's a series of different sub issues with it. So with primary alkyl chlorides, for example, you get rearrangement. So this is a common product. So let's talk about some issues here. So primary alkyl chlorides, you have rearrangements. So this would be hydride or even methyl shifts. So we're going to see how you can come over that. That can be overcome. Now, yeah, so the evidence. So one of the points of like making a primary carbocation sort of gives me the EBGBs. I don't like that. But some of the evidence to suggest that you actually do form that is the fact that this rearranges to a secondary carbocation, and this is your major product. So I guess conceivably there could be an internal sort of hydride shift at this stage where you went from where this hydride moves over to knock out the chlorine, and that would take you directly to this intermediate here. But that's just a debate for, that's really a debate for later. It's neither, I think it's clear to show that you've got a primary carbocation and it undergoes the hydride shift. But anyway, I just thought I would bring that up. So some of the issues is that primary alkyl halides, you have rearrangements or methyl shifts. So if you're trying to do this reaction, you get lots of side product. It's the major product. So that's problematic. So it doesn't work particularly great for primary alkyl halides. Now let's pretend that we're doing the exact opposite reaction. Let's pretend that we are doing a reaction with a tert-butyl group. So tert-butyl chloride and aluminum trichloride. And so the major product that we should get out of this reaction is as follows. So the tert-butyl benzene. Now, if we do this reaction with exactly one equivalent of benzene and one equivalent of your tert-butyl chloride, the major product, in fact, isn't this. This is the minor product. The major product is this one. So that is the major product. And you may say to yourself, why? What's going on here? So remember, at least when I was growing up, there was something called a line dance where I don't know what goes on in the world these days, but in a line dance, you know, two people would stand across from each other in a line, and then you're sort of moving in a certain direction. And as you get to the end, you basically, you and your partner, you go down and you go back to the other side, and then you sort of dance in this direction. And it's a continuing sort of great fun can be had. Now, chemical reactions, and in this case, you basically got two molecules which are always combining to go down. They're all lined up, right? Chemical reactions aren't the same. It's random chaos. It is, so what would happen is, if you've got your this plus your aluminum trichloride is going to make your reactive tert-butyl carbocation. So that's good. Your aromatic ring is going to attack it, as it should. And you are going to form, after it gets re-aromatized, this product, the one you want, the tert-butyl benzene. But it doesn't stop there. That's the problem. So if we remember the various functional groups, do they donate electron density? Do they are they electron donors, or are they electron withdrawing groups? Now, one of the few electron donating groups that we really talked about were alkyl groups. These groups donate electron density. So they donate electron density through induction, right? So if we've got our tert-butyl benzene, and we've got benzene. You will notice that the tert butyl group, this is push, all of these carbons can push electron density. So this means that this ring is electron rich, or more electron rich. With benzene, of course, it's just this, it's just as it was. So in your reaction mixture, if you start to form a bunch of these molecules with the tert butyl group, because it's electron rich, these are more reactive than, say, benzene. So remember, in all of these reactions, it's your aromatic ring. You've got some electrophile. It's your aromatic ring which is attacking your electrophile, which means that the more electron density you have, the better nucleophile it will be. So once you install that tert butyl group, it all of a sudden activates the ring so it can react again. So this then becomes more reactive, and it will react preferentially compared to the regular benzene. So when you do this reaction, that's why this becomes the major product. Because once you start to form it, then it wants to react again because it's more, that ring has got more electron density. Now, there's ways to overcome this. The best way to overcome this is to just use a massive excess. So you need an excess of your benzene. So if you want to make the minor, if you want this to be the major product, then you just use a massive excess of benzene and one equivalent of, so your limiting reagent becomes your tert butyl chloride, and any excess benzene, the non-alkylated stuff, you're going to recycle it. So that's basically how it works. So even if you've got a carbocation which is which is easy to form, this step here would be very easy to form. There's still some side issues associated with that. So it's kind of, so this alkylation reaction has got, there's some challenges to it. But because it's making a carbon-carbon bond, chemists have tried to overcome these challenges. So if we're ever doing a reaction in the, like, if you ever see a question on a test where it's benzene plus tert butyl chloride, we're assuming that we've got the stoichiometry right to make the monoalkylated product. So this is just a sort of sidebar, but it is important. So just assume that if this is the reaction we're doing, let's see here. Then our product is going to be this. So we're adding on this part here. Oh boy. Okay, looks like we'll talk about the acylation reaction on Thursday. And then we're going to talk about substituent effects. Hopefully my computer doesn't, I don't know what the problem was because it just started working. Hopefully it doesn't go through this repeated crashing scenario here. But anyway, that's what we'll do on Thursday. I missed the time. And so the recording for this lecture might be a bit messed up a bit. And yeah, I'm posting the aromaticity one as soon as we're out of class. I forgot that I didn't do it last week. Okay, so this is basically a scanning through of all of the stuff we would have covered today. All right, and I guess I'll see everybody on Thursday. I might send you an email in class today at some stage. I'll do that. All right.